Hello. This lecture will cover pages 145 through 148 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Integrated Circuit Specifications, Part D, Tri-State Outputs. Starting on page 145, in the last lecture we talked about open collector outputs and how they solved the problem of not being able to tie together standard TTL outputs. With open collector you can tie them together, but you had to provide an external pull-up resistance, whether it's an actual resistor or a device like a motor. That device allowed the output state to be pulled high. Tri-state buffers are another way of tying outputs together. With tri-state devices, you have three states. Now, you can have tri-state OR gates or tri-state NAND gates, but we're going to look at the tri-state buffer. Tri-state implies three states. You can have a state that's on, you can have a state that's off on the output. In other words, you can have a high or you can have a low on the output. That's always been the case. But we're going to add a third state. We're going to add a high impedance or a floating state. Here's what a tri-state buffer looks like. Notice it has a second input. It has an enable. So let's take that enable away for a minute and not have the enable present. We're on page 145. If the enable is not there and it's a regular buffer, then you have a 1 in, you have a 0 in, you get a 0 out. You put a 1 in, you get a 1 out. But let's throw the enable in there where if the enable is low, I don't care what the input is, the output will be floating. And I'll show you what I mean by that in a minute. If the enable is a 1, high active, then the buffer works the way it normally would work. A 0 in, a 0 out, a 1 in, or a 1 out. Now, let's take a look at what this output circuit looks like. It's a totem pole output. This is a totem pole output the way we've always had it. But with tri-state, what allows us to be able to tie another device together? Because we couldn't with standard. If you remember the standard, we had this situation here where we had a standard, let's take a NAND gate, another standard NAND gate. And this is what the output looks for this gate, and this is the output, totem pole output for this. The problem arose whenever this transistor here was in saturation and this was in cutoff. This went to a 0. Over here, when this is in saturation and this is in cutoff, that went to a 1. And you couldn't put a 1 and a 0 on the same line because you got enormous current to flow down through here. It was sourced from here, from VCC, and it sunk down through Q4 here on this side, and it took out these devices. And you couldn't, same thing over here. You couldn't have this in saturation and this in cutoff, trying to get this a 1, and have this one here cut off and this in saturation, trying to get this to a 0 because you had enormous current this way, and you take out these devices. So what if we were able to turn this transistor off and this transistor off at the same time? That would give us a tri-state. In other words, let's pretend that this is a tri-state device and it has an enable here, and we turned the enable off. There's additional circuitry built into the tri-state devices back in here, that allows you to do this. It allows you to turn this device off. Turn this device off. Same thing over here. Turn this device off and turn this device off. So they're open circuits. And that's called your floating output. You can see it's like a floating line. It's called your floating output. So what happens, let's go back to here. Look at it. We have the enable in here. And here's a table. And we have our tri-state outputs. The tri-state devices have additional circuitry that allows for a floating output. So let's say we want an output to be low, V out to be 0 volts here. Well, let's look at what the state of Q3 has to be and what the state of Q4 has to be. What about Q3? Has to be cut off. Q4 has to be saturated. What about down here? We want 5 volts out, a 1 out here. Q3 has to be saturated. Q4 has to be cut off. What about the floating state, which we've never seen before? The enable takes care of that on all the different types of gates. When you have it floating, that enable will turn off that gate. In this case, it'll put a 0 up here to turn off that gate. That's a high active enable. So you make that go low. What will that do to Q3? It turns Q3 off and turns Q4 off. They're both in cutoff. That's called high impedance, because with this off and this off, looking back in here, you have real high impedance to ground. This is an open circuit to VCC, and it's an open circuit to ground. That's called high impedance or high resistance state. That's how they work. Now, they also come as a low true enable. This is pretty popular here, where you have a bubble here, and that's just called that's a tri-state buffer, but it's a low active enable. If you want to float the output, you make this high. If you want to enable this to work, you make it low. Let's take a look at page number 146 for a minute. Let's expand this to more than just one line. Let's make maybe 8 lines. Put 8 of these in. In one register, you can put 8 of these devices in. So let's take a look. Using a block diagram, I think it's easier to see on page 146. We have register A, which has 8 bits, a byte in it. We have register B, we have register C, and we have register D. There's 8 lines here. And this is a tri-state register. When we enable this, device with an enable signal, it'll put whatever's here out on the line. Whatever 8 bits are here, it'll put out on the line. Register A will do the same thing, register B will do the same thing, and register D will do the same thing. So we have what we call a control word. This is a micro word or a micro instruction. And how do we make up the micro instruction? LA, here's your LA. Load accumulator, load register A. Here's enable A, enable accumulator A. And here's load B, enable B. Just going across here. Takes care of the first nibble. Let's go over here now. Load C, enable C. Load D, enable D. Keep in mind that when you enable something, it puts data on the bus. When you enable a register, it takes what's in the register and puts it out here on this bus, this tri-state data bus. Matter of fact, it's an 8-bit tri-state data bus in this example. When you load something, you take data off the bus. If you load the A register, you're taking it from the bus to the register. You're loading the register. If you're enabling register A, you're enabling it out onto the bus. So I explained that here, the difference between enable and load. So here's your micro word or your micro instruction. It's generated to move data around the microprocessor chip. What if you want to take the contents of what's in register A and you want to put it in register B? What's the micro word have to be? Well, you have to enable A. You have to enable A. That's a 1 there. And you have to load B. You have to load B. It's a 0, 1, 1, 0, 0, 0, 0, 0. So I'm just going to write that in hex. The microcode to take the contents of A and put it in B is a hex 60. 6, 0. See if you can do this one. See if you can do this one. On your own. Try to do it on your own. Here I want to take the contents of, let's do this. I want to take the contents of C, so I want to enable C out onto the bus, and I want to load it in A. Okay? So I want to enable C, and I want to load it in A. The rest are all 0. What is that? That's a 44. How about this one down here? I want to, you can only enable 1 at a time, but you can load many. Let's take what's in the B register, the contents of the B register. That's what this means. Microcomputer symbology. That's contents of the B register, and you want to put it into register C and D. So you want to enable the B register. And we want to put it into we want to load it into C and D. Oops. Enable the B, load it into C, load it into a D. And what do we have for a micro word in hex form? A 1 alpha. And all you do within a microprocessor chip is you just move data around between registers through micro instructions by enabling and by loading data into the accumulator, into the output register, into the arithmetic logic unit. But let's take this up a notch to a simple microprocessor architecture that's on page 147. Sort of hard to read this, I realize that, but let's take a look at the micro instruction, the micro word or the micro instruction down at the bottom. Notice that there's a C sub P and an E sub P and an L sub M bar. Some of them are high active, some of them are low active down here, but you can, with the exemption of the clock and the clear signals, which we'll talk about in about 4 weeks, let's take a look. Here's C sub P. That's count the program counter. This is what steps you through your program on a microprocessor chip. It's just a counter. Here's your C sub P, high active, count your program counter, and you can enable the program counter to put it out on the tri-state bus here, 8-bit bus. You load the memory address register. There's your low active MAR. Chip enable. Chip enable is low active, and that's how you put RAM out onto the bus. Then you can just follow your load and your enable signals the whole way down here and then starting at the top, with the exception of the clock. And notice your micro instruction is 12 bits here. It's not simple micro instruction of what we have 8 bits before. It's a little more complicated. But what you're doing with this micro instruction is you're enabling data out onto the bus and you're moving it around, putting it into a register, and you're fetching and executing programmed instructions. You just fetch and execute. And the data just dances within the microprocessor chip at many, many hundreds of thousands of times per second. It's just a series of fetch and executes. And how does it do it? It does it through tri-state data buses. So this gives you a rough idea of how tri-state's used. It's allowing these outputs to all be tied together. There's nothing wrong with that. Because when you want to put the program counter out on the bus right here, everything else is disabled. You're not trying to put anything else out there. Everything else, when you look in, is floating. Both transistors are here. There's 8 transistors in this B register. And if you don't have this B register, let's take a look at this. Let's take a look at the accumulator up here. If you don't have the accumulator enabled, if this E sub A bar, or E sub A, if this high active enable the accumulator signal is not high, if it's low, then both of the transistors Q3 and Q4 on all 8 of these lines are off. So this is floating. So it's not encouraging the bus to go high or low. So you enable one thing at a time out onto the tri-state bus. But you can load many things. You can take things off the bus with no problem when you load them into the register. And that concludes the lecture.